Welcome. In this lecture on nonlinear data analysis, we'll explore positive definite matrices. The main concepts for this lecture are: what is a positive definite matrix? What's the quadratic form or the energy term? What's the covariance matrix of given data? And a problem that we can think of as we go through this lecture is, how do data vectors vary from each other? Here's partly a recall and partly a consider. Suppose that we have a symmetric matrix B that has m rows and m columns. We know already from previous sessions that every eigenvalue of this matrix B has to be a real number. We'll refer to a positive definite matrix as a symmetric matrix where every eigenvalue is strictly greater than 0. A positive semi-definite may include 0 for an eigenvalue. One example is certain adjacency matrices that we've come across have this property of being positive semi-definite. A related property is the energy of a weight vector. And what this is a colloquial term. What it means is, for any matrix M that is square and any non-zero U, the quadratic form is the matrix pre-multiplied by the transpose of the vector and post-multiplied by the vector. And so this is a scalar quantity, and the question is, are there restrictions on the values that this scalar can take on? And the answer is that for a positive definite matrix, the energy term or the quadratic form has to be strictly greater than 0. The way that we'll write that is using the successor operator. You can think of it as a curvy greater than sign. We'll write a positive semi-definite matrix. This is one where any non-zero vector u has a quadratic form that produces a value that's greater than or equal to 0. And we'll use this curvy greater than or equal to sign to indicate that this matrix B is symmetric and positive semi-definite. The eigenvalues of a symmetric matrix can be used to characterize this matrix in general. And these are the conditions. We've already briefly stated and explored the idea of being positive definite, which is that the quadratic form is strictly greater than 0. The corresponding statement is that every eigenvalue has to be strictly greater than 0. For a positive semi-definite matrix, the quadratic form is non-negative, and likewise every eigenvalue is guaranteed to be non-negative. We won't use these very much in linear data analysis, but there are corresponding definitions for negative definite and negative semi-definite. The one that's of note is when a matrix is referred to as being indefinite, what we mean is that there are no restrictions that we can determine on the quadratic form or on the energy term, depending on your terminology. And in particular, what that means is there's at least one eigenvalue of an indefinite matrix that's strictly positive, and there's at least one eigenvalue of the indefinite matrix that's strictly negative. If the matrix is larger than 2 by 2, it's possible that 0 is an eigenvalue, but for it to be indefinite, we have to have one eigenvalue strictly greater than 0 and one eigenvalue strictly less than 0.